Now that we know what the equations of lines and planes look like, we can find equations for distances from a point to a line or from a point to a plane. So let's start with the distance from a point S to a line through some point parallel to some vector. And so if we have the equation of the line, the parametric equation of the line, we'll be able to find some vector v. We'll know the vector v on the line. We could plug in some value of t and find a particular point. So if we're given some point S over here and we want to find the distance from S to the line, you can see the shortest distance would be to come into this line exactly perpendicularly, because if you came in at an angle that wasn't 90, then you must be going too far. You could always move the angle closer to 90 and you'd have a shorter distance. So we want to find this distance. Now if we were given the point and we have a point on the line, we could always find this vector PS here. So this is the vector PS, and you can see if this is the angle theta between V and PS, then this distance has to be equal to the length of vector PS times the sine of theta. That's the distance d that we're looking for. Now we actually know how to use an operation to find the length of PS times the length of V times the sine of the angle in between them. That's the length of PS cross V, right? So the length of the vector PS cross V, if we find that length, we know that that's the length of PS times the length of V times the sine of theta. What we're looking for, though, is the length of PS times the sine of theta. We don't want the length of that vector V in there. So we could divide both sides by the length of V, and we get that if we do that, then we get PS, length of PS sine theta. So what this is telling us is that if we want to find the distance, which is the length of PS sine theta, one way to do it without having to measure an angle and then take a sine is just to compute this cross product. So we'll take the length of the cross product divided by the length of V, and that will do it. Let's look at an example of how this could be applied. So recall our formula from the previous slide here was to find the distance from a point to the line. You take PS cross V, V is a vector that lies parallel to the line, and you divide by the length of that vector. So in this case, we have a point, its name is S, it's located at 451, and we have a line. Now what we need to do is we need to find a point on that line, and we need to find a vector that's parallel to that line so that we can apply this formula and find the distance. But we can read that vector off pretty easily, because if you break this up into part that involves t, right, and a part that doesn't involve t, 1, 4, and 5 here, you can see that we have 3, negative 2, 1, t plus 1, 4, 5. You know that we got the parameterization of a line by doing a vector that was parallel to the line times t plus a vector to a point on the line. So that was our parameterization. We can just compare these two and see that the vector parallel to the line is 3, negative 2, 1. You can also see this is a point on the line. If you take, in particular, if you take t equals 0, that's a point on the line. So we have a point on the line is 1, 4, 5. Now that's a lot of steps just to see that the vector parallel to the line is formed just by the coefficients of t, 3, negative 2, and 1. And then if you want to point on the line, set t equal to 0, and you'll get the point 1, 4, 5. That's just the constants. Now we can use this formula because we can calculate the vector from P to S. So to go from P to S, we go from 1, 4, 5 to 4, 5, 1. So from 1 to 4, 4 minus 1 is 3. From 4 to 5, 5 minus 4 is 1. From 5 to 1, 1 minus 5 is negative 4. This is the vector from P to S. And remember, our picture is, here's the line, here's a vector V parallel line, this is a point P on the line, here's the given point S, and we're calculating this vector PS in order to eventually get to this distance D. Okay, we've got PS and we've got V, so now I think we're ready to calculate PS cross V. So to find PS cross V, we can just remember the formula from doing the determinant. I, J, K. PS has entries 3, 1, negative 4, and V has entries 3, negative 2, 1. So the vector we get, let's see, I times 1 minus 8. 1 minus 8 is negative 7. Then j, remember, is in a negative position, but we got to multiply it by 3 minus 12. So 3 minus 12 is 3 plus 12, that's 15. So since j is in a negative position, we'll make it negative 15. And then k, we have negative 6 minus 3 makes negative 9. Before I go on, I'll just check and make sure I didn't make an error in the cross product by dotting the result with the two original vectors. I know it's got to be perpendicular if I've done this correctly. So we have negative 21 and negative 15. That would make negative 36, but then negative 9 times negative 4 is positive 36, so the dot product with PS is 0. Let's check it with V. Negative 21 plus 30, that would be 9 minus 9 is 0. So I feel pretty confident that I didn't make an error because I did get a vector perpendicular to both of those. Alright, so finally we just have to find the length of PS cross V. The length of PS cross V is going to be equal to 49 plus 225. 15 times 15 is 225 plus 81 all over the length of V, which is the square root of 9 plus 4 plus 1. Okay, now we can just add these up. If I borrow this one from the 80, I've got 50 plus 225 is 275. And then I can add the 80 in there. That's going to be 355. So we get 355 all over the square root of 14. Okay, so we've got now the length. We probably should rationalize the denominator, but we've done the calculation that we needed to do to find the distance to this line. Okay.